Hello. We finished glycolysis and fermentation in the previous videos, so let's see how glycolysis is regulated or some thoughts about how it is regulated. Um, so the glycolytic, let me move myself again, sorry. So the flux, and by flux again, we mean the material flow per unit time. So what goes through glycolysis, um, the best way to imagine is like flux is like a river. Okay, the bigger the river, the Mississippi or the Amazon, the more the flux that goes through that river, that pathway. So as far as rivers go in cells, glycolysis is by far the Amazon. Okay, it's huge. It's by far the highest flux of any other pathway, maybe 20 times more even that of protein synthesis, which is pretty robust. And um, the definition of glycolytic flux in this case, if you want molecularly, is the rate of provision of ATP per one pyruvate made. Okay, so how fast it makes ATP for every pyruvate that is made. It's really material flow per unit time. In addition to that, and that's a very key point when we discuss strategies of why glycolysis is the way it is, or flux through the pathway, is that these enzymes are found in huge amounts. Of course, as you've learned from Biochem 410, Biochem 1, you know that the more enzyme you add in the reaction, the faster the reaction is going to happen, right? So one way to increase the flux is to really have a ton of enzyme around, and these just 10 proteins that make up these enzymes that we discussed um, can take up as much as maybe half of the total protein content in the cell. This is what happens in yeast. Of course, yeast loves to do a lot of glycolysis, but in most cells, it's very similar. So, you have the rest of thousands and thousands of proteins in the cell, and they maybe can equal, the fraction of glycolytic enzymes in terms of the total amount of protein. So a lot of energy is going into making actually glycolytic enzymes, and that becomes important. Glycolysis is not all about breaking down glucose, of course, as we discussed. The pathway operates in reverse when you need to make glucose in gluconeogenesis, we're going to see. And at least 6 of the intermediates, and we've already mentioned that, they are starting points for the building blocks, key building blocks for biosynthesis, for amino acids, and so on and so forth. So if you ask how do you know? I mean, how much actually makes it down pyruvate as opposed to serve as building blocks to make other things? Well, you can label the carbons of glucose and see how much of that label makes it down, let's say, to phosphoenol pyruvate or pyruvate. And you have 160 units, whatever the number is here, and about a little less than 2/3 will actually make it all the way down. The other, we saw even the hydroxyacetone phosphate and glyceraldehyde triphosphate are precursors for lipids. So who knows what the cells do with all these intermediates, but a huge fraction, even in actively dividing and proliferating, let's say E. coli, I think, yes, E. coli in these cases, actually doesn't go all the way down. Okay, it gets distributed to other pathways based on the intermediates. So this is what I mean by flux and how much of the material flow goes through the pathway. So it is important to remember the biosynthetic purpose of glycolysis. Now, how do you control it? We keep talking about PFK and the gateway, the rate limiting enzyme, and so on and so forth. For a pathway like this, it's really impossible to regulate by a single enzyme, and the reasons are obvious. Everything operates in steady state, far from equilibrium, but in steady state, and which means by definition that steady state, all the steps are going at the same rate. Okay, there is no slowest rate limiting step. Everybody is the same. So the emphasis again should be on the rate flux of the whole pathway, the flux of the whole pathway, not whether it changes by different and how it changes by different perturbations. And I can tell you now, we've done some of these experiments in my lab, and others have tried this, trying to make glycolysis to increase the flux, let's say by giving it more PFKA, for example, overexpressing. And by overexpressing any one single enzyme, you get nothing. Nothing changes. You have to overexpress all of them, and then you get some increase in the flux. Okay, which gets to point one here, that at steady state, every step goes at the same rate as everybody else. If you look at the delta G's for all these reactions, you see that most of them actually operate at near equilibrium, like the delta G is 0. You have here hexokinase, PFK, where you spend ATP, you have now delta G being different. They're all coupled, and in the end, everything works. But they are operating very close to equilibrium, so you have the additive effect of delta G's and make everything happen. Now, mind you, however, that this is a little bit of a simplistic, just coupling delta G's is not enough to predict flux and efficiency of the pathway. And in fact, metabolic control analysis, this is often the textbook. What I described here is a textbook view. Okay, that's how glycolysis is efficient and everything. But actually, if you more recent efforts to measure these things and see what is predictive, okay, about the flux of the pathway, which is what matters, is not actually even this delta G calculations. The reason goes back to this point. They don't take into account the energy expenditures of the cell to maintain super high levels of these enzymes. So you have to take that into account, and it becomes important as we'll discuss alternative strategies, different patterns of glycolysis in different kinds of cells. So the picture is complex, and you have to, the bottom line, you have to take a holistic view of the whole sequence of events and how much energy you put into making these enzymes at the first place as well. All right. So this is what I had to say about regulation. We're going to stop with this video, and we're going to have another little video to explain its role in cancer. It's extremely important, as it turns out. So, but that's for the next little video. So let's stop here, and we'll come back.